Okay, so we said that the basic two definitions were the first one was given a structure, say M, for some language L. So L has a bunch of symbols, and M is a structure for it. We denote the theory of M is the set of all formulas phi or alpha, or whatever you want to call them, such that M satisfies phi. So it's usually will be sentences, all the sentences, no free variables, such that the model satisfies phi. So that was the notion of the theory of a structure. And you have a question about it in the assignment. And then we talked about the theory of the structure N. So the second definition was more particular. So we fixed an L. So we say let L be a specific language. Then we have function symbols and relation symbols and constants. And in fact, the language could be larger. It would not change the results that we are talking about. And let N be the standard model of arithmetic, which is we have the natural numbers, and F is interpreted as plus, and G as times, as A is 0, and B is 1. So this is the numbers 0, 1, 2, and so on. This is my universe. And we say
You're missing the relation there.
I'm missing the relation. Okay, so you're right. We have to add the relation here. The relation is less than, and then we have 0 and 1. Thank you. And now we say that a structure M for this specific L is a non-standard model of arithmetic so that's the new object that we define if I can write it like this, the theory of M, the theory, say M satisfies phi for every phi in the theory of N, and there exists an element C in the universe of M with infinitely many members of U, members, call them A of this universe, satisfying, A is not good because we have it here, so let's call them Z, infinitely many elements, Z satisfying R of Z C. That is M, if we want to be precise, M satisfies S of R X let's see, R X Y for every S Oh, I thought our exams are arriving. For every S assigning so that S of Y equals dc, and S of X belongs to some A subset of U of M, where A is infinite. So this is kind of a formal way of saying there are infinitely many numbers preceding C in this universe. Okay, so this is my formal way of saying there are infinitely many predecessors to Z. Because we have to talk about what formulas is satisfied, or what formulas are satisfied in this structure. So in this structure, I have the formula Rxy, and I can ask for which assignments S to X and to Y this will hold. So I'm saying if I assign Y, if the assignment takes Y to this element C, then there are infinitely many elements of the structure, so that if you assign X to them, they will satisfy that they're smaller. So it's just a formal way of saying there are infinitely many so this kind of replaces, there is an element S, this was the informal statement, this is the formal statement, so informally C has infinitely many predecessors in M. And we saw last time that such a structure may have a very interesting, some interesting properties, because we know a lot about this structure. So you look a bit puzzled. So just look at it and ask any questions that you may have. I want to say informally that C has infinitely many predecessors in M. But being a predecessor in M just means M satisfies the formula R of the predecessor and C. But in the formula, I cannot talk about elements. In the formula, I can only talk about variables. So the way to translate a formula that talks about variables into a statement about the elements of M is through assignments. So does it make sense? The formula can only have variables. It cannot have in it elements of the structure. But the assignment is what connects between the two. So I have the elements of M, and I have this element here, which is C, and this is my set A. Every time S assigns X to a member of A and Y to C, I will get R X Y. X will be smaller than Y. Yes?
So in other words, would it be appropriate to say that the set A is not definable?
The set A?
So the A that you're saying is not definable in terms of the language?
That's a good question. Why? I mean, why is the set A not definable?
Yeah, I'm just asking, is it?
Okay, so the point is that the set A will be definable if and only if this element is definable.
Oh, I see. So okay.
If I have a definition for this element, it will be the set of all things that are smaller than it. Right?
Okay.
But yeah, it's true that I don't have a definition for this element, but it's not obvious. So I was wondering how you, yeah. We can claim that this element is not definable, but we didn't show this claim. there's no formula such that this element satisfies this formula, and no other element satisfies this formula. Because if there were such a formula, then this formula should have also hold in the standard n. And in the standard n, I don't have such an element. Okay? But I don't want to get into it right now. Okay. So this is our notion of a non-standard model. Non-standard model has this very strange property. And we discussed last time why non-standard models of arithmetic may be interesting. On one hand, it shows the limitations of our logic, but they may be interesting for other respects. So now what I want to show is to prove that there exists an non-standard model of arithmetic. And in fact, you will see from the proof that it doesn't really depend on the choice of language. I could have added things to the language. I could have even added constants to the language for every natural number. It would still not help. But let's first see the proof. Okay, so we want to show that we have a theorem here that says there exists a non-standard model of arithmetic and the proof is by the compactness theorem. So what we are going to do, we are going to consider the set of WAFs, so sigma, which is the theory of n, union a set of formulas here, phi n, such that n is a natural number. And now I have to define those formulas phi n. And those phi n's are going to be formulas in an extended language. So the phi n's are formulas in the language L prime, which is the same as L. I have my F, I have my G, I have my R, and I have A and B, and now I add C. So I extend my language by adding to the language one more constant symbol. So now I'm going to get this sigma is in the new language, is an extended language. And what does phi of n says? Phi of n is the formula that says that there exists x1, there exists xn, such that they are all different. Then we know how to say all different. It just says that for all I not equal j less or equal n, it's not the case that xi equals xj. And on top of it, the formula will require that R for all I, R of x, so let's write it like this, I goes from 1 to n, R of xic. So that's my formula. So what does the formula says? It says there exist n elements, they're all different, and each of them is less than c. I can write it because c is now a member of my new language, so I can write formulas using c. Now, there are two things we want to show about this new sigma. First of all, we want to show that if sigma is satisfiable, if there is a structure that satisfies sigma, then this structure is inevitably a non-standard model of arithmetic. Right? Because if I have a structure that satisfies sigma, it satisfies all the formulas in the theory of n, so it meets the first requirement of being non-standard. And it also meets the second requirement of being non-standard because this element, the interpretation of the element C in the structure, will have infinitely many predecessors with respect to R. Okay, so the next observation is that so let's write it like this. Note that any structure satisfying sigma is a non-standard model of arithmetic. Because it satisfies the theory of n, it satisfies all the formulas in theory of n, and the phi n guarantee that the interpretation of C for every n phi n or m satisfies phi n if and only if C in M has at least n many predecessors with respect to R. So C of M is the interpretation of the constant C in the structure. The structure has an interpretation for every symbol. Our language is L prime has this constant symbol C. In the structure, there will be an interpretation for this constant symbol C. And this interpretation will have infinitely many predecessors. So now to show that we have a non-standard model of arithmetic exists, it suffices, so the existence of a non-standard model of arithmetic now follows once we show that sigma is satisfiable. Right? Because satisfiable means it has a structure. Every structure will be an unstandard model of arithmetic. Now to show it's satisfiable, what tool will we use? The? We don't even have yet a soundness theorem.
Will we generalize induction?
Right. That's another good attempt, right? The compactness theorem, right. So we are going to invoke the compactness theorem. So recall, what does the compactness theorem tell us? That if I want to show that some set of formulas is satisfiable, it suffices to show that every finite subset is satisfiable. So by compactness, by the compactness theorem, it suffices to show that every finite, call it, say, sigma prime subset of sigma is satisfiable. Now, what do I know about a finite subset of sigma? So I have here a sigma prime that is just a finite subset. This is sigma prime. It takes some formulas from here and it takes some formulas from here. So I want to find a structure that satisfies all the formulas that came from the left-hand side, plus all the formulas that came from the right-hand side. And the trick is, note that now should be a structure for the new language. So in this new structure, we will need an interpretation for F, G, R, A, B, and an interpretation for C. So it should be a structure for the language L prime. So just given such finite sigma prime, let n null be the maximum index of a phi I in sigma prime. And such an index exists. Why? Why do I know that there is a maximal one? Because it's sigma prime exists since sigma prime is finite. So now let's define M of sigma prime, a structure satisfying sigma prime, as follows. My universe is going to be the natural numbers. F is going to be plus. G is going to be times. R is going to be less than. A is going to be 0, and B is going to be 1, and C is going to be just the number, say, n0 plus 1. So, what? Right. B is going to be 1, and C is going to be n0 plus 1. You see, so what I do here is I just look at the usual model of structure. This is 0, 1, 2, and here I have this n0, n0 plus 1. And this is the usual structure of the natural numbers. I just say, OK, let's say this guy is the interpretation of C. If this guy is the interpretation of C, it satisfies all of those formulas that say there exist at least so many x's below me. Because I picked this number to be far enough to overcome all the finite requirements that are in sigma prime. So this is a very kind of typical use of the compactness. I can satisfy every finite requirement. Therefore, by compactness, I know that there should be an interpretation for the full set. Interpretation for the full set will have my interpretation of C being an unstandard element. And you see, I needed to add a new term to the language. Because otherwise, I mean, what would happen if instead, so first of all, everybody, we've completed the proof here. So any questions about the proof so far? Yes?
Do we have, maybe I missed something, but do we have to show that n sigma prime satisfies the usual theory of n?
Yeah, I mean, I'm saying I have to argue, I have to claim it. But why does it satisfy the usual theory of M? Because this is the structure N. Nothing changed. The fact that, you see, what I have here is the structure N. I just gave another nameless element, I gave it a name. In the language, initially, I only had names for 0 and 1. So now I have the same group of elements with the same relationship between them, with the same functions and everything. Just I took another member and told him, you now have a name. You're called C. So you're right. We have to add the statement. Of course, every formula in sigma prime that came from theory of n is satisfied because this is actually n. It's the same structure. Right. Okay.
So it's, wait, so we defined n sigma prime, but that's different for every sigma prime as subset of
Right.
sigma. But how do you prove that such n for sigma as a whole exists?
I don't. I use the compactness theorem. The compactness theorem, that's what it saves me. It tells me if I can show that every sigma prime has a structure, then I don't have to worry about the whole sigma. That's what the compactness tells you. That's the magic of compactness. If we can handle every finite sigma prime, then automatically we know that we can handle the full sigma. Although, you see, the structure for every m sigma prime, I'm using the same natural numbers over and over again. For the whole sigma, I will not be able to use the old natural numbers. So it almost looks like a cheat. For every finite substructure, I use the same thing, the same old n. But now I know that the whole set is satisfied, and now I know it cannot be the whole n, the old n anymore. Yes?
I was wondering if we have an example of M that is a non-standard model.
That what?
That M that is a non-standard model.
So we discussed it last time. I mean, an example in the sense that we could describe it.
Okay.
We describe it because the non-standard model, it looks like this. It looks like the usual standard model of arithmetic with the usual operations. And then you have here a dense set, nicely ordered set that looks like the rational numbers. There is no first element, no last element. Between any two, there is another one. And each of them, if you look at it microscopically, it looks like z. It looks like the integers, which are both negative and positive. And we have this whole big collection of them. So this is kind of the way these models look. But this could be very, very, very long. I mean, it could be. And I could have, instead of q, have here the real numbers. It will not notice the difference. I just need here a linear set with no first, no last element, which is dense. Yes?
When you prove that the element of sigma prime is satisfying the theorem of n, is that because they're using the same universe?
Yes. We're using the same universe. We are using the same interpretation of plus, times, less than a and b. So for all the constants, for all the symbols involved in n, we're using exactly the same. The fact that we have another interpretation for another symbol doesn't affect the theory of n, because the theory of n did not mention this new symbol.
So it's hold by vacancy?
What?
Hold vacancy, the actual constant? Or
It doesn't hold vacuously. It holds, what do you mean?
so you said that the actual constant exists in n, but it wasn't mentioned in the theorem of n, right?
The theory of n is in the old language that didn't have c.
Yeah, that's why.
Right. It didn't mention c. So since when we don't mention c, the structure that I use here is the old n. If we don't have a name for c, this is the old n. So let me make two more comments just to clarify where is the catch here. So one comment is, what would happen if I would have tried to avoid introducing a new constant and will just write as my phi n's, I will just try to write it like this. I will write, two comments on the proof. So one is, what would happen, what will the proof still go through if for each phi n we use the formula there exists y and there exists x1 up to xn such that, and here I will say all xi are differ, and y is greater than xi for all I. So this is almost the phi n that I used, but now I'm not using a new symbol. So now I'm looking at the sigma being the theory of n, union all of those new phi n. So let's call them phi prime n. What would be, will the structure for this be a non-standard model? If I did not introduce a new name, and I just said there exists some element which is bigger than all of those. So what would be a structure for this? The natural numbers. Now suddenly, n themselves, the natural numbers themselves will satisfy this sigma. I will not have to add anything. Because for each phi n, I could take, you want someone that has at least 10 predecessors, take the number 11. You want someone that has 1 million predecessors, take the number 1,000,001. You want something that had 2 million, take 2,000,001. Because by introducing the new constant, I forced this y to be the same y for all of them. Otherwise, for every such phi n, I could pick a different y. And the natural numbers would have satisfied it. Yes?
But from the new way, what I don't understand is when we actually picking the c in the original proof, we actually are picking different c's. Because n naught plus 1 is constantly changing on different.
For showing, for every finite sigma prime, we pick a different c.
Yeah.
That's fine. I just want to show that every sigma prime is satisfiable. Once I show that every sigma prime is satisfiable, I get by compactness that the whole thing is satisfiable. To satisfy the whole thing, I need to get one structure, one interpretation of C that satisfies everything. Okay? So my other comment, it's a bit confusing because it really plays on this game between language and interpretation. Let me make one more comment, and then maybe I'll show you something similar. Okay. So one more comment that I want to make. What would happen if you see, I'm trying to nail down the natural numbers. I'm trying to describe the natural numbers. So maybe I could take a language which is much stronger. And in this language, I will have a name for every natural number. And so now what will happen if I take L, let L be this, let's call this L, I don't know, L explicit. And this will be the language in which I will have F, I will have G, I will have plus, I will have times. But now instead of just having, I will have R, but instead, oh, come on. Don't let me write nonsense. I will have R, but instead of just having A and B, I will have infinitely many constants. I will have constants A0 for 0, A1 for 1, A2 for 2, AN for n, and I'll have here AI for every I. And that will be my language for the natural numbers. And now as my model of natural numbers, I will have pinned everybody down. So this universe is natural numbers. F is plus, G is times, R is less than. And this guy is 0, this guy is 1, this guy is 2. And so now every natural number has a name in the language. My language is much richer. Right? Will we have a non-standard model for the theory of this? You see, now, so let's call it n explicit. It's a different structure. It's a structure in which the language is much richer, and we nailed down a name for every natural number. Now I'm asking, do we have a non-standard model? Is there a non-standard model for n explicit? That is, a model for the theory of n explicit in this big language that has a name for every guy, in which some member has infinitely many predecessors. What do you think? Now that I extended my language and I have a name for every single one. So how shall we? And the point is, I mean, the answer is yes, and the trick is that what I cannot say in my language is every x. I would like to say, for every x, I would like to say something like that. For every x, there exists ci such that x equals ci. Right? But that is not in my, I cannot have a quantification over a constant. I called it ai. And for every x, there exists an ai such that x equals ai. This is not a well-found formula because I quantify not over a variable. And if I would try to say for every x, x equals a0, or x equals a1, or blah, 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 what will be wrong with this formula? It's an infinite formula. So this also will not be correct. So I cannot avoid the creeping in of these new elements. And now, in order to build a non-standard structure, it will be even simpler. All I will have to say is my phi n, my new phi n's will just have to be, it's not the case that c equals an. That's all. My requirement phi n will be c, the new guy that is not in the language, the new element in the new language, is not an. For each n, I will have a formula phi n. If I satisfy all of them, my c must be a new guy. Yes? What were you going to propose?
I propose that since all the numbers are named into a constant, so there will always exist an such as c equals an.
In this structure, for every x, there is some an that corresponds to it. But in the non-standard structure, it will not be the case. Right? So what I'm saying, even if we gave name to all the numbers, it will still not avoid the creeping in of the new structure, because we cannot write this infinite formula saying x is equal to one of them. Okay, so I want to move on to a new topic, but I'm not completely sure that this proof was clear enough. So let me just give you an outline for a different statement, and then I'll leave the details for the next assignment, for the last assignment. So the statement I'm going to claim is that the set of, it's a very kind of similar nature. So here what I have a claim is that the family of all connected graphs is not definable. So what I want to show is that, and this is in the language, say, in the language L that just have one two-place relation for the edges of the graph, as we have seen before when we discussed graphs. And the trick here, so there is no set of formulas such that all the connected graphs satisfy it, and every graph is not connected does not satisfy it. Now, what is a connected graph? Just to remind you, a connected graph is a graph in which, so let us consider undirected graph for simplicity. So a graph is connected if for any pair of nodes that I will pick, I can find a path that connects them. That's the definition of connected graph. So this is a connected graph. If I add here something, then suddenly this graph is not connected. Okay, so a graph is connected if every 2 points, two vertices in the graph have a path between them. And I'm claiming we cannot write a set of formulas that will be satisfied only by connected graph and not by not connected graph. And the proof will use a kind of a similar idea. And the idea will be to extend the language. So the proof idea is consider a set of formulas sigma in the language L prime, which is the odd language with R, but now I add two constant symbols, A and B. So I expand the language and write a set of formulas in this new language. And the set of formulas in this new language, sigma, is going to be the set of all phi n in n, where phi n states that there is no path of length n from A to B. Okay, so this sigma says, I mean, if I have a structure that satisfies sigma, then this structure is not connected. Why is it not connected? Because the interpretation of A and the interpretation of A of B cannot be connected. For every n, I cannot find a path of length n between them. So every structure for sigma is not connected. But now, so just note that every structure for sigma, so a structure for sigma looks like a graph that has vertices, it has edges, but it also has interpretation for A and B. That's a structure for sigma, right? It's a graph with vertices, edges, and interpretation for A and interpretation for B, which are specific vertices. Every structure satisfying sigma is not connected. Since A in this structure is not connected to B in this structure. For every, if there was a path, this path would have been of some length n. But phi n states there is no path of length n between these two. So every structure for this sigma is not connected. And now we assume assume by way of contradiction that some set of formulas gamma defines the family of all connected graphs, and consider sigma union gamma. And we ask, is this satisfiable or not? So is sigma union gamma satisfiable? No, because this one says the graph that satisfies me must be connected, and sigma says the graph that satisfies me must be disconnected. So I cannot satisfy both of them together. But now by compactness, I can satisfy every finite subset. Because every finite subset will say, oh, there should be a connected graph, and the interpretation of A and the interpretation of B should be at least n steps apart. That's okay. I can find a model like this. So we get a contradiction by using the compactness. And it is similar in the sense that in both cases, I needed to add constant symbol to the language in order to construct my counterexample of a set of formulas. So I will put some more of this stuff in the next assignment, and hopefully you will all do it so well that I'll feel comfortable of putting such a thing in the exam. But yeah. Okay, I want to move on. So we have this wonderful compactness theorem that causes a lot of trouble, but it is also very useful to have it. And in some sense, the compactness theorem, we will see it, is just a consequence of the fact that we have a proof system such that every proof is finite and it is sound and complete. And this is definitely a requirement that we would like to have. Right? So what I want to show next, I want to switch from the semantics back to the syntax to talk about a proof system. But just to make the connection, just note that if we have a proof system such that I use the delta because I think that's the notation that the Anderton book uses. Let delta be a proof system. So this is a set of axioms and deduction rules such that the following three requirements hold. First of all, sigma soundness, which means for every set of WAFs, sigma and every formula phi, if from sigma I can prove in this system phi, so I use this delta to say proof in this system, formal proof in the system, then sigma logically implies phi. So this is soundness. If from the assumption sigma, using my proof system, I can prove phi, it means that every structure that satisfies sigma should also satisfy phi. This is the same soundness that we had in propositional logic. Okay? Requirement 2, I want to have completeness. So anybody can tell me, try to phrase completeness. So remember, the soundness and completeness connect the syntactic proof system to the semantics that we have. Right? So we say, assume you have a proof system that has these nice properties. So what is completeness? Yes?
Every satisfiable well-formed formula has a proof.
Not just being satisfiable. Being satisfiable, it means that in some structure it holds. So we want something stronger. You remember, it's not that every satisfiable phi in propositional logic. I cannot prove the formula P. P is satisfiable. But so what do we need to require? Not every tautology, right? So here it will just be the reverse of this. For every sigma and phi, if sigma logically implies phi, then sigma can prove phi. For sigma being empty, this implies that every logical truth is provable. So, I mean, we've seen exactly those properties in propositional logic. There's nothing new here, except that when I say here sigma, I mean a set of formulas in first-order logic. When I say logically implies, I mean every structure that satisfies this, instead of meaning every truth assignment. But other than that, it's the same thing. And now I want the third requirement. And the third requirement is that every proof in the system delta is finite, which is also a very natural requirement. We don't want to have infinite proofs, because if we have infinite proofs, we'll not be able to check that it's a proof. Okay? Now I'm claiming, assume that you have those three properties, then we have compactness. Then we have the compactness theorem. So the compactness theorem follows from, although it looks like so undesirable and such unpleasant consequences, it follows from those very desirable requirements. That you have a proof system that is sound and complete, and every proof is finite. So how does it follow? So I have a claim, so let delta be such a proof system. If such a proof system exists, then it implies the compactness theorem. So I claim that the existence of a proof system with those desirable three properties implies the compactness theorem. So you remember in propositional logic, we proved the compactness theorem without having to invoke any formal proof system. We did it completely in the semantics. Here, my easiest way of proving the compactness is through the proof system. So proof of the claim. And the idea is the first step is to show first step, and this first step is going to be exactly like what we did in propositional logic, is that we define the notion of consistency, just as we did in propositional logic. So I say that sigma is consistent if for some alpha, sigma cannot prove alpha. And we know that equivalently, for no alpha, sigma proves alpha, and sigma proves not alpha. So we have exactly the same definition of consistent that we had in propositional logic. Again, you have a proof system, you can define consistent. I cannot define consistent without, so it's all with respect to my proof system delta. I cannot define consistent without a notion of a proof. Consistent is a syntactic notion, it has to do with proving. But we can repeat the same definition, just pull it over to first order logic. So we have the notion of consistent. And then step 2, second step, and this is also pretty easy, I mean, pretty much like we did in propositional logic. Now we can prove using soundness and completeness that sigma is consistent if and only if it is satisfiable. And again, the proof will be word by word the proof that we did in propositional logic. Because there was nothing in this proof that had to do with a specific choice of axioms. Now that we have those two steps, we can show the compactness. How do we show the compactness? I want to show you, you have to recall what is compactness. So anybody can now tell me, remind me what compactness is? What is the compactness? Yes?
If sigma is satisfiable, then every finite subset of sigma is also satisfiable.
Almost. Just it's not. It's the other direction that we care about. If every finite subset is satisfiable, then sigma is satisfiable. It's actually if and only if, but what we care about is if every finite subset is satisfiable, then sigma is satisfiable. That's the tool that we were using over and over again. So our third step now that we have this tool, prove the compactness theorem. So how are we going to do it? So note that so far we only used the first two requirements from our proof system, which was soundness and completeness. I didn't make any use yet of the requirement that every proof is finite. But now what I can do is have this table. I don't remember if I showed you this diagram in the propositional logic or not. I will say sigma is consistent. We know by step 2 that sigma is satisfiable. Now, sigma is consistent is equivalent to every finite sigma prime subset of sigma is consistent. And this is due to the property 3. Because if sigma is inconsistent, then there is a proof of alpha and not alpha. This proof is finite. So I can collect all the assumptions of the proof into a finite sigma prime, and sigma prime will already be inconsistent. So for this part, all I use is the fact that every proof is finite. If every proof is finite and sigma is inconsistent, there is some finite sigma prime that is already inconsistent. It's an argument that we already seen in the propositional logic. Now, I will use again the equivalence between being consistent and being satisfiable. So I get every finite sigma prime subset of sigma is satisfiable. So I got the compactness. Sigma is satisfiable if and only if every finite subset is satisfiable. So what we see is that those compactness can be thought of as trouble, but because it shows us that many things are undefinable, it shows us that we cannot even define the natural numbers, that the non-standard models creep in, but it is inevitable if we want the very important property of having a proof system which is sound, complete, and every proof is finite. And all of those 3 steps are exactly what we did in propositional logic. We can repeat the proofs word by word, just have a different interpretation. Whenever I say sigma, it's a set of first-order formulas. Whenever I say provable, it's provable in this delta that I haven't showed you, the proof system for first-order logic, and so on. So are there any questions at this point? Okay, so now the next natural step is to show you what should be such a proof system. So that will be our next step. I want to describe a proof system that is sound and complete for first-order logic. Now, I mean, the course is running towards its end a little bit too fast for me, but so we will prove the soundness, we will not prove the completeness, because there are so many interesting topics that I still want to cover. I mean, the main interesting topic, 2 interesting topics that I still want to cover. One is the connection of this logic to programs and program verification and things like that. And the other one is Gödel's incompleteness theorem. Did I mention it at the beginning of the class? Right. Which is a very exciting and philosophically stimulating theorem. So for the sake of this, I will give you the proof system. We will get a little bit feeling of how to work with it. We'll show soundness, but we will skip showing the completeness. Okay, so that's our next step, a proof system. So a proof system will be very much like the proof system that we saw in propositional logic, except that now it is a real proof system. It's not a toy. It's not a Monopoly game. So a proof system for first-order logic and it is going to be designed according to the same set of rules that we had before. We'll have axioms, and we have deduction rule, and the deduction rule will be the same modus ponens that we've seen in propositional logic. But the axioms will be a little bit more complex. So we will have axioms and deduction rule, which is going to be modus ponens again. And then we are going to look at I of axioms deduction, just like we did in propositional logic. A proof is whatever is a generating sequence in this inductive structure. Okay, so what are the axioms? So the axioms are going to be divided into groups. So the axioms are going to be divided into groups, and actually the axioms themselves, I have to define them inductively, but I will postpone the inductive step here is almost trivial. Okay, so what are so the first type will be substitution, any substitution of WAFs for variables for propositional variables in a propositional tautology. So my first set of axioms are any substitution. So I will have here axioms like, examples could be things like, say, for every x, phi of x arrows, there exists a y such a psi of y. So this in itself looks very strange, but I can say this or not for every x, phi of x arrows, there exists a y such a psi of y. So now, when I look at all of these things, I don't care what are phi or psi. I can say this is the formula that I substitute for p. And here I have not p. And p or not p is a propositional tautology. So this is an axiom. So whenever you can take a propositional tautology and replace every variable with a formula, same formula for the same variable whenever it occurs, the first tautological formula that you get is an axiom of type 1. And notice that, I mean, we have to all the time when we talk about axioms, all the time we have to make sure that one important property, I mean, we have soundness and completeness. These are two requirements from a proof system. But do you remember what was the third important requirement from a proof system? Finite. Finite was a manifestation. I mean, finite is what we talked about now, but it's a manifestation of a more basic requirement. And the basic requirement was checkable. That you can check what is a proof and what is not a proof. In order to be able to check what is not a proof and what is not a proof, you must be able to check what is an axiom and what is not an axiom. And here it is not difficult to check. Because what I'm going to do, if you give me some formula and I want to check if it is an axiom of type 1, all I have to do is to see how far can you give me a formula, I ask how far can I break it down just using the propositional connectives. So if I can break it, say, by arrow and get here psi 1, psi 2, phi 1, phi 2, or I can break it by an and so on. But at some point I will get stuck. This is what will happen here. I'll take this formula and try to parse it out to see what is the tree that generated this formula. It will break here in the or, but this will no longer break just using propositional variables. So once I finish the parsing according to the propositional connectives, I can check, I can put here P, Q, T, whatever, for every formula that I get, and check if what I get is a propositional tautology or not. How do we check if something is a propositional tautology or not? What?
Prove it, truth table.
Truth table. Yeah. I mean, the simplest thing is a truth table, right? So there is a way to check whether a formula is an axiom of type 1 or not. You parse it, but you don't break quantifiers. You only break it according to propositional connectives. And then when you get stuck, you substitute and see if you get a tautology. Okay? So that's the first type of an axiom. The second type of an axiom, so note that this gives me infinitely many axioms. But I can check what belongs to this group and what's not. Okay? My second type of axiom is the axiom that says for every x phi, every formula of the type for every x phi implies phi of tx. Okay, so every WAF of the form. So I have to explain to you what is phi of tx. Yes?
To prove something, is it not to show that it's a tautology?
What?
To prove something, is it not to show that it's a tautology?
Okay, that's an interesting question. I know I can address it from all kinds of directions. Tautology is a semantic notion. Proving is a syntactic notion. So proving means you have a sequence of formulas. To prove alpha, you have alpha 1, alpha 2, up to alpha, such that each of them is either an axiom or follows from someone before by modus ponens. That's one step. Second step is say, okay, if we have soundness and completeness, then everything that we prove is a logical truth. But here we have to distinguish. This is a propositional tautology. So we take our formula, we put a variable, positional variable for every term, and we ask, do we get a propositional tautology? This is very limited. It doesn't give you all the logical truths. So for example, if we look at the formula, look at just and it's a good question, but look at the formula that we showed that it is true. We showed that it is true that if there exists a y such that for every x are xy, then for every x there exists a y such that are xy. Right? We know that this is a logical truth. Right? We know that if there is someone that everybody likes, then everybody has someone that they like. Okay? But what happens if I try to break it down, just parse it to propositional variables? It breaks here. Here I get for every, there exists a y such that, so that for every x are xy. Here I get for every x there exists a y such that are xy. And I cannot break it any further by just using propositional connectives. Now, let me call this guy P. And now when I come to this guy, I ask myself, is it exactly the same thing syntactically? No. So I have to give it a new name Q. So when I break this formula down to propositions, I get P arrows Q. Is it a tautology? No. So I have a logical truth, which is much richer notion than by breaking it down propositionally, I get a tautology. Okay? So the distinction here is between a propositional truth to a logical truth in our richer language. Okay? Okay, so it seems that we are done with our time. So we have one axiom. I will explain the second axiom when we meet on Tuesday next week.